Hey everyone, this is a video lesson that I'm using in my AP Calculus AB class, and I'm putting online in case it would be helpful to others as well. There is a link to a printable set of guided notes in the description of this video that you can use to follow along with the problems as I do them in this lesson. In this section, we are going to begin to discuss differential equations, how to solve them, basic ones at least, and how to represent them with what are called slope fields. Okay, I get made fun of for saying that this is one of my favorite sections, so I won't say it, but you know, it is. Okay, all right, I said it. All right, so let's start with something that you should already know. Okay, this doesn't look too scary, right? That title slide looks scary, I admit. But this shouldn't look scary. If the derivative equals sine of x, then what is y equal to? If the derivative of y, I should say, is sine, then what is y? Okay, it's the antiderivative, right? Which is negative cosine of x plus c. Does that look familiar? I hope so. Okay, so there's three different things that we can say we just did right here. Three different ways to describe the calculus that we just did. We could call it finding an antiderivative. We could say we are solving an indefinite integral. We could write it as the integral of sine of x dx, and it would be equal to negative cosine of x plus c. And here's the new one. We can call it solving a differential equation. Congratulations, you just solved your first differential equation. And that's the new thing that we're going to discuss in section 6.1. So what I need you to know about differential equations, and if you're one of my students, hopefully you already explored this a little bit with the chapter intro, is that a differential equation is an equation that contains derivatives. Okay, so if you have derivatives in your equation, you are working with a differential equation. It relates rates of change. So, you know, anytime you're doing all those related rates problems, you were writing differential equations. And solving a differential equation means finding a function that satisfies the differential equation. Now, that last line doesn't tell you a whole lot about how to solve them, right? But, you know, I want you to think about an example like this. Okay, if I tell you that the derivative of y with respect to x is equal to y, okay, that's a common differential equation, and I tell you to solve it. Okay, there's all sorts of things that you could do, and we're going to talk about those things in this section to solve that equation. But also, if you could just think about to yourself, what function would satisfy this equation where, you know, if you read this, it says the derivative is equal to the function, right? The derivative of y is equal to itself. Which function has that property? Are you thinking what I'm thinking? Who knows? Who knows what you're thinking? But I'm thinking about y equals e to the x. That satisfies that equation, right? The derivative of e is itself. And so we could say that if we have y equals e to the x, then we know that dy over dx is equal to e to the x. And that works here, right? E to the x equals e to the x. I'm basically like plugging in these pieces here to show that it works. Okay, so, you know, that is something that you can think about as you're working with these equations. Does it work? When you solve, does it work in the original equation that you were looking at? Okay, so I'm just going to go ahead and admit that example 1 is not my favorite way to start, but you got to start somewhere. Yes, I'm saying that one of the things that we're doing here is not my favorite thing to do, but that's just because the outcome, I guess you could say, is a little bit anticlimactic. Okay, but they are real life scenarios where we can write differential equations. Okay, let's take a look at example 1a. Barometric pressure P, measured in millibars, changes with respect to altitude A, measured in feet above sea level, at a rate that is directly proportional to the altitude. Okay, I think the wording is a little bit confusing right there, but what it's trying to tell you is the rate at which barometric pressure is changing is directly proportional to the altitude. Okay, we will use lowercase a. It's not like explicitly stated in here, so we should probably state it. We're going to use lowercase a for altitude. And directly proportional means if you take some, like, you know, they differ by a constant. So if you take some constant times the altitude, you get the rate at which the barometric pressure is changing. Okay, we don't know exactly what the constant is, though. So we are just going to say directly proportional to the altitude could be represented by the expression k times a. okay? Now, on the other side of the equation, it's not P equals K times A because of this word right here. It's the rate that is directly proportional to the altitude. And so we want to show a rate of the barometric pressure with respect to the altitude. And the way that we would write that as a variable is dP over dA. Oh, look, it does say altitude A right there. I completely missed that. Sorry. All right, there you go. Anyway, that's the answer to example 1A. The rate is directly proportional to the altitude, can be represented by dP over dA equals K times A. Can you tell why these are my favorite? All right, part B. For the first 9 months of life, the average weight W in pounds of a certain breed of dog increases at a rate that is inversely proportional to time in months. Okay, so we have two variables going on, W and time, but this time inversely proportional to each other. Well, the rate is inversely proportional to the time. And inversely proportional would mean like a constant divided by time. Okay, so that's what we need as an expression on one side of our equation. And on the other side, you are going to show the rate at which the weight is changing with respect to time as a derivative dW over dt. All right, we can check off that little requirement. These types of equations are more fun in different scenarios, but just writing them like that, I don't think it's that exciting. But let's move on to something that I do think is exciting now. Take a look at this. To find a particular solution to a differential equation, we need an initial condition, like an ordered pair that the function passes through. Okay, so I've talked a little bit about solving differential equations. If I give you dy over dx equals sine of x, you tell me y equals negative cosine of x plus c, you solved the differential equation for what is called a general solution. Okay, so that's actually another thing that we can add to our list up here. We solved the differential equation, but what we really did was we found what's called a general solution. Okay, so now what about finding a particular solution? Take a look at example 2. Find the particular solution to the equation dy over dx equals e to the x minus 6x squared, whose graph passes through the point 1, 0. Okay, so here's the steps that you can take fully to show your solution path to a differential equation. Okay, so I'm just rewriting the differential equation. And then what I'm going to do is I am going to separate the dy and the dx like we did back in chapter 4 when we were working with differentials. Okay, I'm going to move the dx to the other side like that. The next step is if I want to solve from here, I am going to take an integral of each side. Now, on the right-hand side, I think we're pretty comfortable with how to do this, right? We look at what's in between the integral symbol and the dx, and we find the antiderivative. The antiderivative of e to the x is itself. The antiderivative of 6x squared, let's use our antiderivative power rule there. Add 1 to the power and divide by that new power. So that'd be minus 2x cubed, right? Plus c. Notice the integral symbol and the dx did not come down. We solved that part by finding the antiderivative of what was inside. Okay, but what do we put on this side? Well, this is the function, so we put y, right? We will put a y right here, but here's why. In between this integral and this dy symbol is a 1. And the antiderivative of 1 with respect to y, in terms of y, is y. The antiderivative of 1 is x usually, right? But in this case, because this says dy, the antiderivative is y. Okay, and this is called your general solution again. Whenever you get an antiderivative with a plus c, you call that a general solution. Now, we are going to use the point that was given to us. 1 is the x coordinate, 0 is the y coordinate, subbed in, looks like this. And what do you think that's going to do for us? It solves for c, right? It finds the particular c that we would need if we want our solution to go through this point. Okay, so let's see. Let's write this C as a decimal. Okay, we could write an exact C value, but we'll write a decimal. E to the 1 is 2.71828. This is 2. So we're taking 2.71828 minus 2. So we're at 0.71828, right, plus C. Subtract that on each side, and we have negative 0.72, if we want to round it, equals C. Oh, man, my brain was just, I almost boxed that in like that, as though that's the answer. That's not the answer. Okay, that's just the C value. Okay, here's the final answer. The particular solution is y equals e to the x minus 2x cubed minus 0.72 as the C value. There we go. So your particular solution is the same as your general solution, but with a value in for your C. Okay, so let's try another one, even though this says you try. Oh, okay, never mind. I have the answer there. Okay, let's try another one, even though it says you try. I'm going to go ahead and explain this one as well. Okay, find the particular solution to this differential equation, dy dx equals 5 secant squared x minus 3 halves root x. Or I'm going to write that as 3 halves x to the 1/2 power, because I'm going to use antiderivative power rule there again as well. Okay, if you feel like you can do this one on your own, go ahead and pause the video and then just move forward and check your answer with mine. But I'm going to go ahead over all of the steps again, just because it's a little bit new. Okay, so let's move the dx over to the other side. And take the integral of each side like that. Okay, now that you know what happens here, this part's easy, right? This is just going to become y. On this side, we need an antiderivative. The antiderivative of 5 secant squared, the 5 carries down because of the constant multiple rule. The antiderivative of secant squared is tangent. So we have a tangent x right there. Now for this part, remember, you need to use your antiderivative power rule. Start with your power of a half, add 1. Okay, a half plus 1 is 3 halves. Take that new power, and it is what you divide by to get your coefficient. So 3 halves divided by 3 halves is 1, or negative 3 halves divided by 3 halves is negative 1, plus C. Again, notice the integral doesn't carry down, the dx doesn't carry down. We're done with those symbols because we did that operation. Now let's take the particular point, x is 0, y is 7, and sub those values in to find a particular C. That should be a 0 right there. That should be a C. Okay, so tangent of 0 is 0. This all becomes 0, which means C is 7. And so from there, don't box in that answer like I almost did. You're going to write your particular solution. This is the general solution. I forgot to label that. I'm just going to write GS for general solution. I usually like to label that because then I can go back and find where I labeled that to rewrite it as the beginning of my particular solution. 5 tangent x minus x to the 3 halves power plus 7 is our particular solution. Okay, so far, solving a differential equation is taking antiderivatives, right? Not so bad. But sometimes you're going to come across differential equations that you can't solve so easily. Take a look at example 3. It says, find the solution to the differential equation f prime of x equals e to the negative x squared, for which f of 7 equals 3. Keep in mind, this part is just giving you an ordered pair again, an x comma y, that the graph goes through. I'm going to change my color. So what do we do in this case? Okay, well, let's talk about a couple of different things we can do. First, we could use part 1 of the fundamental theorem of calculus to sort of pretend that we're writing an answer. Take a look at my little note here that's in red. Use the form f of x equals the integral from a to x of f prime of t dt plus c. Okay, so what we're doing here is like saying, all right, we want to find the f of x function, but we're not really sure how to do that. So what we're going to do instead is just call it the integral of this. But let's change the variable to t and put the x in the upper limit. Okay, finally, where's the ordered pair come in? Well, the x coordinate becomes your lower limit, and this 3 is your plus c. So there's your particular solution in example 3. I know, it's just like sort of piecing together something that doesn't really tell you much at all, though, right? So that leads us to something that's very exciting, slope fields. Okay, so what we need to talk about now is how you can take a differential equation and create something called a slope field from that equation. Okay, and what that can do is it can show a graphical representation of your general solution. Okay, and it can be helpful for when a solution cannot be found by integration techniques. So if you look at the little example that I have here, the differential equation that generated the slope field is dy over dx equals sine of x. But if you would like sketch along one of these curves, okay, you see like a whole bunch of curves here, right? Little lines that when you put them all together, they form a curve. I'm going to try to sort of sketch along one like that. Okay, what you're actually looking at in that solution curve is not the graph of sine of x. You're looking at the graph of negative cosine of x, right? Oh, that should be down there. Oh, well, it has a weird plus C. Okay, anyway, you're looking at the graph of negative cosine x from the differential equation of sine of x. Okay, let me show you what I mean. Take a look at this one. Okay, let's go to the differential equation being cosine of x. Example 4. Construct a slope field for dy dx equals cosine of x. Okay, what you do here is you take all of these ordered pairs where you see the dots, and you're going to substitute them into this differential equation, dy dx equals cosine of x, and you're going to get a number out for each ordered pair, like this. At this ordered pair, let's use blue. At this ordered pair of 0, 0, the most important thing is the x coordinate here, because I need to sub something in for x. And so if I know that the x coordinate is 0, I can sub that in here. And what I get out of that, cosine of 0, is 1. What I do with that value is I draw a little tangent line at that point that looks like it could arguably have a slope of 1. So I'm going to go to 0, 0, and I'm going to say, like that. There's a little tangent line that I could say, that looks like it has a slope of 1. Okay, and I could go up to this point, and it has the same x coordinate, right? It has an x coordinate of 0 again. There's no y in this differential equation, so we don't need to worry about the y coordinate. So it would also have a slope of 1. And here would be a slope of 1. And I'm trying to make these parallel, all showing a slope of 1, but sometimes it's hard. Okay, and so this is saying here's what the tangent lines could look like for any of the curves that could go through this point. Okay, and then we just move on to other points, and we do that like this. Let's call this column pi over 2. Let's scale our axis like this: pi over 2, comma pi, or pi over 2, pi, 3 pi over 2, 2 pi. And then negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi. Okay, so for the next x coordinate, we need cosine of pi over 2. And that could go for any of these points because they all have the same x coordinate of pi over 2. What's that? That's 0, right? Cosine of pi over 2 is 0. So at this pi over 2, I draw a little tangent line that has a slope of 0, horizontal. and at this one as well, because it's the same x coordinate, and at this one, and at this one, and at this one, and so on. Okay, let's move over to the next column where we're looking at pi. Cosine of pi is -1. So now I'm going to do slopes that I could say have a slope of -1. They would be decreasing like this. And you just continue with all of your different points until you get the slope field. And what you're going to see when you're done, look at that, is a graph that if you follow along, if you start at one place and you sort of follow along with it, it will be a solution to the differential equation, okay, like this. Or, doesn't have to be there, it could be like this. And notice that those curves are not representing cosine curves, they're representing sine curves. So this is showing you y equals sine of x plus c graphically. It's showing you the solution to the differential equation graphically. Okay, so when you have differential equations that are just in terms of x or just in terms of y, they're not too difficult to construct. Okay, I'm going to warn you, example 5 is a little bit tedious because here we're constructing a slope field for the differential equation dy dx equals x plus y. And we're going to sketch the graph of a particular solution that passes through the point 2, 0. Okay, when you have both x and y in your differential equation, then the slope of each line that you draw is going to be dependent on both coordinates in the ordered pair. So it is a little bit trickier, okay, but I'm going to try to show you a way that you can approach this systematically, and then I'll show you what the answer looks like. So, you got to start somewhere. I usually start at the origin, so I'm going to say, okay, at the point 0, 0, what do I have? Okay, also, you could change dy over dx to m if you'd like to remind yourself that what you're calculating right now are slopes. Okay, 0 plus 0 is 0. So what you are going to do at the origin is you are going to draw a little line that has a slope of 0, like this. Okay, but all of the rest of the points along this vertical column are not all going to be a slope of 0 this time, right? If I move up 1 point and I'm at the point now, the ordered pair 0, 1, the slope is now 0 plus 1, which is equal to 1. So I'm going to draw a line that has, what I could say is a slope of 1. Okay, when I move up to 0, 2, I'm looking at a slope of 0 plus 2 or 2. So I need to make it steeper. Now, don't get too bogged down in worrying about, well, is that line exactly a slope of 2? Don't worry about that. You just need to say it's steeper than 1, right? 0, 3 would be a slope of 3, which would be a little bit steeper. Sometimes I mess up and I don't make it look very good, and it's okay. It'll still all come together, I promise. 0, 4 is even steeper and even steeper here. So you can see that as you go up, because the y coordinate is increasing and the x is staying 0, those get steeper and steeper as we go. Okay, and then the opposite, well, they're going to get steeper, but in the negative direction here. 0, 1 is -1, right? So same steepness about like that one, but decreasing. -2, -3, -4, -5, something like that. Okay, there's your first column done. Now from here, you can decide, do you want to do another column or do you want to try to find a diagonal of all of the same slopes? Because sometimes you can find that. Here's what I mean. If you're adding x and y, then, anywhere that you have opposites, like 1 and -1, 2 and -2, you're going to have a slope of 0 there, right? 1 plus -1 is 0, 2 plus -2 is 0. So you could say, okay, let me find 1, -1. That's going to be a slope of 0. 2, -2. 3, -3. 4, -4. 5, -5. And this direction as well. -1, 1. -2, 2, and so on. Find all of the slopes that are 0 and do those first. Okay, again, you're going to need to decide as you do it for yourself, what do you think is the best route to take to draw in all of the slopes that you need. Okay, and when you are done, you get something that looks like this. Isn't that cute? Yeah, I drew in all those lines. It's crazy. All right, let's not talk about it. All right, finally, when your slope field is done, you sometimes maybe will need to draw in a particular solution. Okay, this one says to sketch the graph of the particular solution that passes through the point 2, 0. So what you want to do is you definitely want to find the point 2, 0. Okay, and you want your graph, your curve to go through that point. Okay, but what you don't exactly know from there is what are other points that it goes through. So don't get bogged down too much in worrying about that stuff. What I usually say is just try very hard to go with the flow and don't pass over asymptotes. Okay, here's an additional little note. When drawing a particular solution to a slope field, draw a continuous functional curve, making sure to pass through the given point. So you definitely want to go through that point, and you can kind of see that what you're going to be doing on the right-hand side is you're going to be going up like that, right? Increasing and getting steeper. Okay, what are you going to be doing on the other side? Well, there's definitely a turning point because we have a slope of 0 going on along here. And then I actually think that what's happening here is an asymptote. So I'm going to try to just go along that and not cross over it like this. Maybe, something like that. It works. As long as you are attempting to go with the flow and you go through the point, your particular solution is going to be okay. Next, now that we've talked about how to construct slope fields, you can do some matching with slope fields. Okay, we can definitely do one of them because we just looked at it. Would you agree that A is that one, right? We just did that. All right, but let's talk about how to analyze these a little bit further in order to be able to match them up. Okay, so it says use slope analysis to match each of the following differential equations with one of the slope fields A through D. Do not use your graphing calculator. There are slope field programs that you can get for your graphing calculator that draw them for you. We usually do them in this class, but I don't know if we'll do it this year or not. Okay, but anyway, here's the first thing that I do. I look for a differential equation that just has an x in it. Okay, so this one, dy over dx equals 0.5x minus 1. And what I know about that is that all of the columns that you see will have the same slope, like this. Notice that these all have vertical columns of the same slope, and they all have the same x coordinate. And so B has to match with 0.5x minus 1 because this differential equation is only in terms of x. Okay. The opposite is true for whenever you have a differential equation that's only in terms of y. It will be horizontal rows that will have the same slope because, like this one, these all have the same y coordinate. And finally, with these other ones, you would want to do a little bit more thinking usually. Like we know that A matches up with this one because we just did it, which leaves this with D. Okay, but there's other things that you can do. You can look at particular ordered pairs and think about what the value would be when you sub them into x and y for your differential equation to help you figure out the other ones. We're going to do a lot of practice with this in class, so I think you're going to get pretty good at it. Okay, and finally, the last thing that we need to talk about for this section are solving what are called separable differential equations. And these are equations where you are going to see both x and y in the differential equation, and you're going to be able to solve it. Okay, but first we need to know what is a separable differential equation and what types of differential equations with x's and y's are not considered separable. Okay, take a look at the examples. In A, I have a couple of equations that are separable. And here's what I mean by separable. They can be written in this form. a function of y dy equals a function of x dx. Okay, technically like this, but we're going to separate them to look like this. Okay, so in this first one, if I multiply both sides by the y and I multiply by both sides by the dx, I would have y dy equals 2x dx, and that means that this equation is separable. This one is also separable. It's just going to look a little bit different because I have to divide both sides by this y and again multiply by the dx. So this one would look like this. dy over y is equal to 2x dx. And technically that's of this form because I could pull the dy over to the side and write it as 1 over y dy equals 2x dx. So it matches up with this form, and that's how I know that it is separable. Okay, these ones are not separable because what I would have to do to move the y over to the other side is subtract it. Multiplying by the dx, though, would not eliminate it from the left-hand side after that, and you would just have a big old mess. I mean, I usually say to my students, try it. Try to separate, meaning the y's with the dy's on one side, and the x's with the dx on another side. Separate your variables separate. And after a while, students see how much of a mess it becomes and they realize that you can't. Okay, the key thing here is when your x's and y's are being multiplied or divided, it is separable. If they're being added or subtracted, it's not. Okay, if they are separable, then you can solve them using the same process that we discussed at the beginning of this set of notes. Take a look at example 7 with me. Solve the separable differential equation dy over dx equals 2x over y, and we will eventually use this condition to get a particular solution. Okay, so we're going to start by multiplying the y over with the dy and the dx over with the 2x, so it looks like this. Next, we are going to take an integral of each side. Okay, this time, though, on the left-hand side, you're not going to end up with a y because you have a y in here. So what you now need to do is say, what is the antiderivative of y? It's 1/2 y squared, right? Just like the antiderivative of x is 1/2 x squared, the antiderivative of y is 1/2 y squared. On the other side, what is the antiderivative of 2x? That's x squared. And you have to pick one side to put your plus c on, not both sides. Think about what would happen if you put plus c on both sides. It could cancel, right? We don't want that to happen. So what we typically do is we put the plus c on just the x side like that. Okay, and that c represents the constant of integration for both of these put together on the right-hand side. Okay, there's your general solution. Not too difficult, right? Now let's use this ordered pair. -1 is x, 1 is y, subbed in like this. To solve for c. And subtracting 1 on both sides would give us a c value of -1/2. So our particular solution is 1/2 y squared equals x squared minus 1/2. Now, usually it's fine to leave your answer like that, even for the purposes of the AP exam. But I will tell you, just in case you would see a multiple choice question where the y is solved for, you could sometimes see the y solved for, and it would look like this. Okay, we can multiply everything by 2 to get rid of that 1/2, and then square root, and we could have the square root of 2x squared minus 1. Okay, that's just another way that you could see your particular solution. Oh, okay. So I'll talk about this when we get into class. You know, when we say multiplying by both sides, multiplying by dx on both sides, it's a little awkward because, like, technically you're not multiplying, but it works. But that's something that we'll talk about in class. That kind of surprised me that that was in here. Okay. So there's a you try, and as usual, if we were in class, I'd probably say try it for yourself. But also, this one is a little bit trickier, so I'm going to go over it with you in detail right now. Okay, the first thing that I suggest is that you multiply the dx over, and let's just make it look like this. dy equals 6y squared dx. Okay, now, oh, I lost my x, sorry. dy, let me try that again, equals 6y squared x, from right there, dx. Now, we need to get this y squared over to the other side, and that is actually the only part that needs to go over. The 6 does not need to stay with the y squared. So you could divide both sides by the y squared and write dy over y squared, and keep the 6 with the x on the right-hand side like that, 6x dx. Okay, but before we take an integral of each side, let's do something with this divided by y squared. Let's rewrite it as y to the negative 2 power times dy. And that just makes it look a lot better for when we need to find the antiderivative. That's what we're going to do now, take the integral of each side. Okay, keep in mind, antiderivative power rule on this side says you need to add 1 to your power, so that would be a negative 1 power, and then that will divide by that as your coefficient out in front. So the antiderivative of y to the negative 2 is negative 1, or just negative y to the negative 1. On this side, the antiderivative of 6x, what's that? 3x squared, right? Plus c. Put the plus c on the x side. Now let's use this ordered pair. 1 will go in for x, 1 over 25 will go in for y to solve for c. One over 25 to the negative 1 is just 25, so there's a negative in front. That's negative 25. This is 3. Subtract 3, and you get negative 28 is equal to c. Okay, so here's my general solution before I subbed in the ordered pair. I'm going to rewrite that with negative 28 in for the c. Okay, and finally, this is fine as a particular solution answer for me, but just so you know, you could see it solved for y, and it would look like this. Okay, so either one of these would be fine. Okay, finally, one more example to show you, and I want to, in particular, look at this one where we do solve for the y, because I think it makes more sense when we do. Take a look at example 8 with me to finish up. Solve the separable differential equation dy dx equals 2y using the condition that the graph of the function passes through the point 0, 3. Okay, so for this one, when we multiply the dx over to the other side, we get, let me try that again. We get 2y dx, and we don't want that y beside the dx, so let's divide it over. So we have this, y over dy equals 2 dx. Okay, again, let's bring this y out of the denominator. This time it would have a negative 1 power on it. And integrate. Now what happens here? What is the antiderivative of y to the negative 1? Do you remember that one? You can't use antiderivative power rule, right? That's the ln. And technically, it's the ln of the absolute value of y. Just in case your y coordinate would be negative. We will talk about that more in section 6.2. Okay, but I need you to know right now, whenever you use an ln as an antiderivative, you're going to put absolute values in it. On the other side, what's the antiderivative of 2? That's 2x plus c. Now let's sub in 0 for x and 3 for y. And what we get is that c is equal to the ln of 3. The absolute value of 3 is just 3, so we can drop the absolute value at this point. Probably thinking, well, why did you even bring it up? Again, it's just a technicality that we'll talk about later on. Okay, so going back to my general solution, which is right here, I'm going to rewrite it. With the ln of 3 in for the c. Okay, so now what do we do from here? Well, this is an answer. Okay, this is a particular solution. You could be done. But again, I want to show you what it looks like when you solve for the y. Okay, when you solve for the y, that means you're going to raise both sides in a power of e like this. On the left-hand side, that becomes y. And on the right-hand side, you can actually split up this sum into a product with base e. E could be e to the 2x times e to the ln of 3. Okay, and the reason that we would want to maybe do that is because e to the ln of 3, that is just 3. Okay, so our particular solution looks a lot cleaner when we solve for y, right? Y equals 3e to the 2x. That's a function we could definitely work with. And finally, anytime you have your particular solution and you want to check it to see if it works, what you could do is you could always just take the derivative of it and see if you end up with where you started. Like this. We had the derivative is equal to 2y. When we solved, we found that y is equal to 3e to the 2x. We can check by differentiating y equals 3e to the 2x. The derivative of 3e to the 2x is 3e to the 2x times 2. Okay, but keep in mind, 3e to the 2x, that's the same thing as y. So we could change this 3e to the 2x back to a y. Oops, I didn't do that there. We could use substitution right here to say 3e to the 2x is equal to y. And we end up with dy dx equals 2y, which is what we started with. So that's how we know it works. Okay, everybody, that is it for section 6.1 on differential equations and slope fields. As usual, I hope it was helpful. Bye.